6.3 is inverse trig. So up until now, we've been plugging in an angle and getting out a value. So now we'll basically be doing the exact opposite. Instead of the answer being a ratio of sides, the answer will be the angle itself. So we're going to understand and use inverse sine, cosine, tangent. Find exact value of expressions using inverse sine, cosine, tangent, using calculator, using inverse trig to solve, and using exact values for composites with inverse functions. When we're taking a trig function, typically what happens is that we'll have, sine of some angle equals a value. Okay, it really equals the ratio of sides. All right, an inverse takes the ratio and finds the angle. All right, so typically we plug in a measure of an angle, we get a ratio. Inverse trig starts with the ratio and gets the angle. So if f of x equals sine x, then f inverse of x equals the inverse sine of x. Okay, remember, inverse does not mean reciprocal. In 1513, we talked about these things called one-to-one functions, and it's where a graph passes both the horizontal line test and the vertical test. Vertical test proves it's a function, which means no vertical line passes through the function more than once. Okay, so on all sine, cosine, tangent, secant, cosecant, cotangent, they all pass the vertical line test. Okay, the one-to-one part means they pass the horizontal line test, which means no horizontal line passes through more than one part of the function. Well, sine, cosine, and tangent are wave functions, so it definitely fails the horizontal line test. So to find inverses, we limit the domain. Okay, we restrict it. For sine, it's restricted to negative pi over 2 and positive pi over 2. That's so that every y value between the min and max, so negative 1 to 1, is represented. For cosine, 0 to pi, same thing. For tangent, negative pi over 2 to positive pi over 2. Okay, so on restricted domains, we can find inverse trig functions. So the inverse sine, there's two ways you're going to see it. Okay, so inverse sine, if I resolve this for x, all right, I get x equals sine y. So the inverse sine function is sometimes called arc sine. Okay, and is labeled as arc sine x. Okay, so these two, inverse sine and arc sine, are literally the same thing. Kind of like how we have y equals f of x. Y is f of x. They mean the same thing. So inverse sine has a domain of I lost my head there for a second. And with inverse functions, the domain and range switch. So the domain for regular sine is all real numbers, but we're switching it. But here's the key is the range is negative 1 to 1. So that makes the domain of inverse negative 1 to 1. And of course, we limit the range. This means these are what our answers can be. Negative pi over 2 to positive pi over 2. All right, and since we're limiting cosine to a domain of 0 to pi, that means the range of inverse cosine is 0 to pi. Those mean my answers have to fall between 0 and pi. And just like sine, two different notations, inverse cosine or arc cosine. Okay, you're going to see it represented as arc cosine of x. All right, that means it has answers. If the domain of the cosine is restricted 0 to pi, the range of inverse cosine is 0 to pi. And then last is tangent. and we can notate it as inverse tangent, arctangent, which is written as arctan. All right, and it has to have answers between negative pi over 2 and positive pi over 2. Okay, now, here's the hard part with inverse sine, cosine, and tangent, is because the answers are restricted. Your answers have to fall between two numbers. They have to fall for sine in negative pi over 2 and positive pi over 2. So we've got a picture of it over here. We have the graph, but I want you to consider it in terms of a unit circle. Actually, make a straight line. All right, so we have positive pi over 2, negative pi over 2. We've got 0. We have positive pi over 4 and negative pi over 4. We have positive pi over 6, negative pi over 6, positive pi over 3, negative pi over 3. So our answers have to fall among these three. All right, whereas inverse cosine, again, I can see the angle here, but I can see that the bottom starts at 0 and stops at pi. So consider the unit circle. That is the upper half of our unit circle, where we start at 0, end at pi. We have pi over 2 in the middle. So I've got pi over 4. And in quadrant 2, because my answers have to fall between 0 and pi, this is 3 pi over 4. Pi over 6. Okay, in quadrant 2, that would be 5 pi over 6. Pi over 3. And in quadrant 2, that would be 2 pi over 3. So all my answers for cosine have to fall between 0 and pi. Okay, now, tangent had asymptotes. So the inverse tangent, regular tangent had vertical asymptotes. Inverse tangent has horizontals. So I'm going to get really close to these, but I'm not going to get to pi over 2. So it is going to be this exact same function. So you're going to copy and paste this. Or just redraw it. Because I don't feel like redrawing it. But it excludes pi over 2 and negative pi over 2. So it's everything except for those two. All right, so in these two examples, we're rewriting as an inverse. All right, so inverse sine goes inside as the ratio. And then we get the angle. So inverse sine of the ratio equals the angle. Okay, same thing here. It's going to be the inverse cosine of the ratio equals the angle. All right, evaluate, give your answer in radians. So these are your unit circle values. Got inverse sine of 1/2. You ask yourself what angle, and that's sine, so it gives me a y. Of 1/2. Okay, well that sine is positive, so we're over here in quadrant 1. The angle that gives me a y value of 1/2 is pi over 6. Okay, inverse sine of -1. Again, this is what angle gives a y of -1. Again, consider that this is our graph here. And sine is negative in quadrant 4. Okay, well, our domain is from positive pi over 2 to negative pi over 2. So the angle between positive pi over 2 and negative pi over 2 that produces a y value of -1 is negative pi over 2. Cosine. Okay, so one angle, cosine is x. Okay, again, consider the graph for inverse cosine, the unit circle. Cosine is negative in quadrant 2. So the graph that provides an x-coordinate of -√3/2, this is 5 pi over 6. Okay, inverse sine, and that's a y value. So I need an angle with a y of -√2/2. Consider your function here. Sine is negative down here. Remember, it's positive pi over 2 to negative pi over 2. Okay, so negative pi over 4. Tangent, I did tell you to memorize these tangent values. Okay, tangent of 1. Okay, so which angle produces a tangent ratio? So produces a y over x. Let me try that again. Which angle has y over x is 1? Okay, so for that to exist, the x and y have to be the same. Tangent has this range, not including the pi over 2's. Tangent is positive in quadrant 1, where x and y are the same, is pi over 4. Cosine of positive 1/2. So this is an angle with x of 1/2. So consider cosine, 0 to pi. Cosine is positive in quadrant 1. That angle with that x value is pi over 3. Okay, so most calculators have inverse, sine, cosine, and tangent buttons. So on the 84, you see above the sine, cosine, and tangent, you have to hit the second button, and then sine. Second button, then cosine for inverse cosine, second tangent. And the trick is to make sure you're in the right mode. So if I'm using Desmos, I'm going to go back and check it says give answer in radians. I'm not graphing. All right, so for Desmos, it's under functions. Let's see, there's sine, inverse cosine, inverse tangent. So inverse sine of 0.97. Go back to main, 1.325. Inverse cosine of -0.4. $1.982. So not super difficult to do inverse sine, cosine, and tangent in your calculators. You just have to double check your mode. Okay, so we've done right triangle trig. That was 5.4. So now we can use right triangle trig to find measures of missing angles. Okay, so just like I showed you, theta, opposite, adjacent hypotenuse. Okay, we don't know our theta. I also don't know the opposite. I do have adjacent, it's 9, and I have hypotenuse, 12. Okay, so the way this works, inverse cosine of the ratio equals the angle. So inverse cosine of the ratio equals the angle. And it says use degrees. So switch that. Inverse cosine, 9/12, 41.410. Okay, and our last one here for this one. Theta, opposite, adjacent, hypotenuse. We don't know theta. It's there, but I don't know what it is. Opposite 6, I don't know adjacent. Hypotenuse 10, so this is sine. So inverse sine of the ratio 6/10 equals your angle. Of your ratio equals your angle. So 36.870. All right, composite functions. You did these in 1513 as well. This means you have a function inside another function. So when you do composite functions, you work your way inside out. So we're going to do the inside. So we're going to do the sine of pi/3. Okay, so sine of pi/3. Okay, I'm keeping the outside. Now I'm answering what sine pi/3 is. Sine pi/3 is √3/2. Okay, now I'm asking for, since it's inverse sine, I'm asking for the angle. With a y of √3/2. Okay, that's going to put us back where we started. And it works that way because the angle that was given is inside the domain for inverse. Just remember the domain for inverse, or the range for inverse, pi/2 to negative pi/2. And pi/3 falls here. So it's inside that. Okay, but this one, this is our domain. Pi/2, negative pi/2. This one's outside that domain. Okay, so I've got to work on it. So we're going to find what's inside. Keep the outside. Evaluate the inside. Sine 2pi/3. Okay, that is, since that's quadrant 2, that's positive √3/2. Okay, I've got to be careful with this. The inverse sine of √3/2, okay, is an angle with a y of √3/2. But inverse sine has to fall in that domain. Negative pi/2 to positive pi/2. Sine is positive, quadrant 1, so that's going to be pi/3. Inverse cosine is from 0 to pi. So I'm going to ask myself, this is the cosine of 2pi/3. Well, cosine of 2pi/3, cosine is negative in quadrant 2. I just lost my train of thought. And the cosine of 2pi/3 is negative 1/2. So now I'm asking for an angle with an x of negative 1/2. Cosine's negative in that quadrant, so that's going to be 2pi/3. All right, so I've got cosine and cosine. My given angle falls in the domain for inverse cosine. So we get what we get. Maybe what if it doesn't? And considering that's the domain. Okay, this is where I can get my answers from. Negative pi over 3 falls down here. So it's not outside the domain. So I'm going to evaluate it differently. Work your way inside. So keep inverse cosine. We're going to do the cosine of negative pi over 3. So that is, pi over 3 is, negative pi over 3 is down here. Cosine's positive there, so this would be 1/2. Okay, inverse cosine of 1/2, that's an angle with x of 1/2, but since it's inverse, it has to fall inside here. X is positive, quadrant 1, well, it's going to be pi over 3. Inverse tangent of the tangent of pi over 8. These are our first 4 examples. These are unit circle values. Pi over 8 is not a unit circle value. So I'm going to perform that operation first. I'm going to go ahead and find the tangent of pi over 8. And that was in radians. So 0.414. So this is the inverse tangent of 0.414. Okay, if we consider the domain for a tangent, well, pi over 8 is like here. All right, well, so what we've seen, inverse sine, if the angle was inside the domain, I got that angle again. Inverse cosine of cosine, if the angle was in the domain, I got the angle again. Inverse tangent of tangent, same thing happens. If the angle is inside the domain, I get that angle again. And then I get here. Inverse tangent of 11 pi over 9. So we're going to do tangent of 11 pi over 9. It's in radians. Tangent. .839. All right, so remember tangent, pi over 2, negative pi over 2, excluding those. 11 pi over 9 is definitely not inside that domain. So, I have to think of something else. So I'm going to do inverse tangent of 0.839. Go back to your main function. We've already done 0.839, so I'm going to hit answer, which is right by the plus sign. And we get 0.698. Now I'm mixing the trig function, so I've got to be more careful here. Inverse sine of the cosine of 13 pi over 6. So I am looking at the cosine of 13 pi over 6. Okay, I can see that it's reference angle. I'm just going to do it down here. It's pi over 6. Because it's got the pi over 6 right there. I just got to figure out where it's at. All right, well, it's more than double. Okay, because double 6 is 12. Right, so that's one more. this is putting me in quadrant 1, where cosine is positive. So that gets me basically thinking about the cosine of positive pi over 6, which is root 3 over 2. Now I'm looking here. So I'm with the angle, with a y, of root 3 over 2. Now inverse sine has to fall between negative pi over 2 and positive pi over 2. Sine is positive here. Okay, the angle with a sine of root 3 over 2 is pi over 3. All right, inverse cosine sine of negative 11 pi over 3. So I'm going to do sine negative 11 pi over 3, or negative 11 pi over 4. So reference angle pi over 4. And I know that because I've got the pi over 4. So now I got to think about where this is rotating and what angle or what quadrant that puts me in. So I know that double the 4 is 8. So one full rotation around is negative 8 pi, or negative 8 pi over 4. So I've got an 11. That's 3 pi. So that's going to take me into quadrant 3. Okay, sine pi over 4 in quadrant 3 is negative root 2 over 2. So this is going to be inverse cosine. Negative root 2 over 2. Remember, this negative root 2 over 2 comes from the fact that we're in quadrant 3. All right. So now I've got inverse cosine, negative root 2 over 2. So this is an angle with an x of negative root 2 over 2. Again, remember that cosine, 0 to pi. Cosine is negative over here. So that's going to give me 3 pi over 4. Okay, now using Pythagorean theorem to evaluate inverse cosine and composite functions. So if I have inverse cosine of 4/5, remember this represents a ratio. So for cosine, that is x over radius. Okay, well, I need sine. Sine is y over radius. I already know what the radius is. It's 5. So what do I need to find sine? I need the y. I'm use Pythagorean theorem. X squared plus y squared equals radius squared. Y squared is 9. So y is 3. That is an assumption I am making because cosine is positive. It doesn't give me any information, so I'm going to keep it positive. So the sine, okay, let me backtrack. All of this represents an angle. All right, because remember the answer to an inverse cosine, inverse sine, or inverse tangent is all an angle. The answer is an angle. And I want the sine of that angle. Okay, well, sine is y over radius. I have the y now. So the sine of this angle is 3/5. We're going to do the same idea here. inverse tangent. Tangent is a ratio of y over x. Okay, so that means I know that the y is 5 and the x is 12. Cosine is x over radius. I'm missing the radius. So x squared plus y squared equals radius squared. So that means radius is 13. All right, inverse trig of anything is an angle. So all of this nonsense right here is an angle. I want the cosine of this angle. Cosine is x over radius. I know x is 12. And radius is 13. Sine of the inverse tangent of 7/4. Okay, so I know this is a ratio, y over x, which means I know the y is 7 and the x is 4. And I want the sine, which is y over radius. So you put that in theorem. (16 plus 49). Is 65. Okay, so I'm going to take the square root. The square root of 65 does not simplify, so we're going to leave it like that. So we go back to the beginning. Inverse tangent of 7/4, that is an angle. Okay, the answer to the inverse is an angle. Now I want the sine of that angle. Sine is y over radius. I know y is 7. And now I know that the radius is root 65. Let me get that radical out. All right, find a simplified expression for the cosine of the inverse sine of x over 3. Because remember, all of this, that's an angle. So I'm really asking for the cosine of some angle. All right, but if I consider that I have inverse sine, it's terrible. All right, let's say that's where my theta is. Sine is opposite over hypotenuse, right? So because I have an x there, I am going to be so careful about using x squared plus y squared equals radius squared, because I already have an x. So instead of using x squared plus y squared, I'm going to use a squared plus b squared equals c squared. Okay, so I'm going to call this one a. And we have x, and we have b. So we're solving for a. So a squared plus x squared equals 9. Subtract our x squared. Take the square root. Now I've got to figure out, is it positive or negative? Okay. So, cosine, or excuse me, inverse sine, pi over 2 negative pi over 2. So inverse sine always falls here. Okay, so that means my angle is in between quadrant 1 and quadrant 4. Cosine is always positive in those quadrants. So A has to be the positive square root 9 minus x squared. So then the cosine is the positive square root 9 minus x squared over 3. All right, find a simplified expression for the sine of inverse tangent of 4x for negative 1/4 to 1/4. All right, so the inverse tangent is an angle. So I'm wanting the sine of some angle. Well, tangent is, let's see. Okay, I'm going to draw a triangle. Tangent is opposite, so it's 4x over adjacent 1. Sine is opposite over hypotenuse, so I'm missing the hypotenuse. I need this piece. Okay, so I'm going to use a squared plus b squared equals c squared. So a squared plus b squared equals c squared. We're solving for c, the hypotenuse. So 4x squared is 16x squared. All right, so c would be the square root of 1 plus 16x squared plus or minus. Okay, so the hypotenuse is always positive. So this is going to be the positive square root 1 plus 16x squared. So now that I know that the hypotenuse is 1 plus 16x squared, I know that sine has to be y opposite, so that's 4x over the hypotenuse. 1 plus square root of 1 plus 16x squared, which we don't love that because you're not supposed to have a radical in the denominator, unfortunately. So it is kind of a nightmare of a problem. So I'm going to get that radical out of the denominator. Which doesn't really, it looks worse than it is. Multiply across the top and across the bottom. Not a whole lot we can do after that point, so it just looks way worse than it is. Kind of is what it is.